Okay, so let's tackle our first projectile motion problem. A ball is hit with an initial velocity of 30 meters per second at an angle of elevation of 30 degrees. Calculate A, the greatest height reached, B, the time of flight, and C, the range. Okay, so before we get stuck into this problem, let's recap what we derived or learned in the first video, which I'll link on the top right hand corner here. So on the vertical plane, the green ball is launched with an initial velocity of v0 at an angle of elevation theta. It's going to follow a parabolic trajectory, and at any point during its flight we can determine the velocity. So the velocity is simply expressed as the initial velocity by the cosine of the launch angle in the I direction plus the initial velocity by the sine of the launch angle minus gt in the j direction. The acceleration is always going to be negative g in the j direction, and g for gravity, and we can determine the position at any point during the flight, and that's given by r of t equals v0 cos theta t in the I direction plus v0 sine theta t minus a half gt squared in the j direction. And we found that the equation of the trajectory is y is equal to x by tan theta minus x squared by g on 2 times the initial velocity squared by 1 plus the tan squared of theta. So for part A, the greatest height reached, let's simplify our diagram. I'm just going to sketch out the trajectory, which has the equation y of x equals x tan theta minus x squared by g on 2 by v0 squared by 1 plus the tangent squared of theta. Well, since the trajectory is parabolic, the greatest height will occur mid-flight. So at this point, the slope of the trajectory, which we get from taking the derivative of the trajectory equation, should be equal to 0. So you may recall that from your studies of maxima and minima. And by the way, this is only one way to find the maximum height. Another way is to set your vertical component of the velocity to 0 and find the time it takes to reach there. But this is my preferred way. So we'll keep going. So if we take the derivative with respect to x of the trajectory equation, we get tan theta minus 2 by x by g on 2 v0 squared by 1 plus tan squared theta. And we set this equal to 0, and we want to find the x-coordinate for when this expression holds true. So if we rearrange that, we get, first of all, 2 on the top and 2 on the bottom cancel. We get tan theta equals x on v0 squared by g by 1 plus tan squared theta. This 1 plus tan squared theta I'm going to rewrite as sec squared theta. So that's according to the Pythagorean identity, that sec squared theta equals 1 plus tan squared theta. And if we make x the subject, we get x equals v0 squared on g by tan theta over sec squared theta. Okay, here's where it gets a little bit tricky. The sec squared on the bottom can be rewritten as times cosine squared theta, by virtue that sec theta equals 1 over cos theta. The tan theta I can express as sine theta over cos theta. And we have a power of 2 that cancels with a single power. So this then becomes x equals v0 squared on g by sine theta by the cosine of theta. Now here's another trigonometric identity that I'm going to put to use. The double angle formula sine of 2 theta is equal to 2 times sine of theta by the cosine of theta. So that would imply that sine of theta by the cosine of theta equals sine of 2 theta on 2. So this becomes sine of 2 theta on 2. So finally, the x-coordinate where the trajectory has a 0 slope is equal to v0 squared on 2g by the sine of twice the launch angle. So this point here, which I shall call x mid, x at mid-flight, is equal to the initial velocity squared over 2g by the sine of 2 theta. And now, just to confuse you a bit more, I am still going to use, so this is now x mid, I'm still going to use x mid is equal to v0 squared on 2g by the tan of theta over the sec squared of theta, as this is what we're going to sub into this equation to find the maximum height. So let's do that, because y max, the maximum height, or the maximum y coordinate, is going to occur at x mid, which equals v0 squared on 2g tan theta over sec squared theta by tan theta minus v0 squared on 2g by the tan of theta over sec squared theta, all squared by g on 2 v0 squared by 1 plus tan squared theta, which of course equals sec squared theta. Okay, simplifying, we've got v0 squared on 2g by tan theta times tan theta equals tan squared of theta. Sec squared of theta, like last time, I'm going to write as cos squared of theta minus, when we take the power into the parentheses, we'll get v to the 4th power, v naught to the 4th power, over 4g squared tan theta squared over sec to the 4th power of theta by g on 2 v0 squared by the sec squared of theta. Tan squared can be written as sine squared of theta on cosine squared of theta, and that means the cosine squared is cancelling on the top and bottom. The 4th power of v0 reduces to 2 and cancels that on the bottom. And for those who have picked up my mistake, well done, because there's not supposed to be a 2 in front of the g here, and therefore the 2 in front of the g here goes, the 4 in front of the g squared goes, g squared cancels with the g on the top to reduce that down to just g on the bottom. The 4th power on the bottom reduces to 2 when it cancels with the power of 2 on the top. So after all that, we have v0 squared on g by the sine squared of theta minus v0 squared on 2g by tan squared of theta on sec squared of theta, which we already know reduces to sine squared of theta. So once we subtract those two terms, we have y max is equal to v0 squared on 2g by the sine squared of theta. And note that it looks very similar to x mid equals v0 squared on 2g by the sine of twice the launch angle theta. One is a sine squared, the other is a coefficient in front of the angle, so be careful of that. So after all that derivation, our problem has the initial velocity as 30 meters per second. The launch angle is 30 degrees, with gravity g being 9.81 meters per second. The greatest height for this particular projectile is y max equals 30 squared by sine squared of 30 divided by 9.81 times 2, obviously, which equals approximately 11.47 meters. So please check that with a calculator. Excuse me, that should be meters, not millimeters. Now part B of the question asks us to find the flight time. And again, I'm going to show you my preferred method, but there is more than one way of finding this answer as well. And that's because projectile motion equations are all simultaneous, so as long as you have a logical approach, you should be able to find the right answer. But we'll continue with my approach, and I'm going to draw out the trajectory again. So we're going to use the position vector, which is r at any time is given by the initial velocity by the cosine of the launch angle by the time in the horizontal plus the initial velocity by the sine of the launch angle by time minus a half gt squared in the vertical. I'm just going to take the vertical component, y of t, so note that r is equal to x of t I plus y of t j. So y of t is equal to v0 sine theta t minus a half gt squared. And I'm going to set this equal to 0 because at the start and at the end the y value is equal to 0. Okay, so at the start the height of the ball is 0, and at the end of the flight it comes to land and the height is also equal to 0. So let's solve for t. If I factor out a t, I get t outside of v0 sine theta minus a half gt, which equals 0. So this means that either of these terms is equal to 0, which makes sense. So we have t being equal to 0 at the start of the flight, or v0 sine theta minus a half gt equals 0. And I'll rearrange this for t to get a half gt equals v0 sine theta. Then gt equals 2 v0 sine theta. And finally, t equals 2 by v0 by the sine of theta on g. So this here is the expression for the time of flight. And for our question, again with v0 equals 30 meters per second, theta being 30 degrees, gravity g being 9.81 meters per second, we have time equals 2 times 30 times sine theta divided by 9.81, and that simplifies to 2 by 30. Sine of 30 is a half on 9.81. The 2 and a half cancel, so all you have to do is calculate 30 on 9.81 and we should get 3.06 seconds. So the final part of the question, part C, is to find the range. And this is the easiest part because we've done all the groundwork in part A. So I'm just going to draw the trajectory again. So the range is defined as the maximum horizontal distance of the flight of the projectile. And of course in part A, we found the value of x mid to be equal to v0 squared by the sine of twice the projection angle on 2g. Well, then it would simply follow that x max, where the projectile lands, the maximum x value, which would equal the range, is equal to 2 times x mid. So therefore, the range equals x max, which equals v0 squared by the sine of 2 theta all over g. So for our particular problem, we've got v0 equals 30 meters per second, the launch angle theta equals 30 degrees, g being equal to 9.81 meters per second squared. Therefore the range equals 30 squared by sine of 2 times 30 over 9.81, and that's equal to 900 by root 3 on 2 over 9.81, which equals 450 root 3 on 9.81. Plug that into a calculator and we should get 79.45 meters. Okay, that will conclude this video. We will be doing more examples on projectile motion, so stay tuned. If you have any questions, please feel free to use the comments below. If this video has helped you, please share it with your friends and study buddies, make my channel famous. And if you can help me make more videos, I'd really appreciate a small donation. There's a PayPal link in the description below. For now, best of luck with your studies, and I'll see you on the next video.